I am Mr. Tarrou. In this video, we're going to introduce what similar polygons are, and we're going to work through 5 examples to help you get through your homework. So, similar polygons. Well, similar figures in general, polygons have to have straight sides, but similar figures in general are just simply multiple figures that have the same shape but can vary in size. Now, they can be the same size, but that's more specific, and we call those shapes congruent. Similar polygons, which do have that possibility of, having, and most of the time will be different sizes, and of course polygons being closed figures with straight sides, must have corresponding angles which are congruent. This is what locks those polygons to be the same shape. And their corresponding sides must all be proportional. So in other words, we have a couple of triangles here, which I have off to the side showed that they are similar. And we have triangle ABC and triangle DEF. Now I'm stating that those are similar triangles, which means they are the same shape, and yet they can vary still in size. Very kind of like the idea of congruence, but with congruent figures, they must be the same size as well as the same shape. So we need to have our corresponding angles congruent. So angle A must be congruent to angle D, angle B must be congruent to angle E, up here at the top, and then angle C and angle F must be also congruent. And of course I've drawn my 2 triangles to be in the same orientation just for ease of notes. But as you look at your diagrams, make sure all those corresponding angles are congruent and that you can name those congruent parts. Now, what we mean here, the corresponding sides are proportional. Remember, we just did a video, or hopefully just studied proportions, which means that you're comparing numerical values, quantities, in a form of division. And when we take the corresponding sides, we need to make sure these are all in the same direction. So I've done AB over ED, or DE. I've done BC over EF, and I've done AC over DF. All of these proportions are set up in the same order. In this particular case, I've gone from what I've drawn as a small triangle to a large triangle, making sure that you go in the same direction every time you set up these proportions that we're going to make sure, check to make sure that they're all equal so that I meet my second requirement for the check of these 2 polygons being similar. These all need to be equal for the shapes to be similar. Now, when you check that all these proportions are equal and you determine that they're all the same value, well then what you deal with, or what you have, is a constant ratio, which is, or are, the scale factor. I mean, there's multiple ratios, but yet there's one scale factor, so it wasn't, do I use is or are, but all those constant ratios are going to be, if equal, the scale factor between the similar polygons. So my example here is, I'm stating that, well, again, I've given you a couple of figures that are in the same orientation, but I've kind of like zigzagged my letters around so that you just don't always think I'm going in alphabetical order. And I have the quadrilateral of ACBD is similar to E, H, F, and G. Well, if they are indeed similar, then when I check that I have a constant ratio every single time, I should get the same number. So if I take 8.5 and divide it by 5, and when I take 5.1 and I divide it by 3, and when I take 6.8 and I divide it by 4, and then as I start to run out of room, 1.7 divided by 1. Now, of course, the last one's kind of a gimme there because I'm dividing by 1. When I check all of these ratios, then as long as they're all the same numerical value, then I have 2 figures which are similar. And of course, again, all my angles must be congruent as well, my corresponding angles. Well, all of these do come out to be a scale factor of 1.7. And I only call it a scale factor because they're all equal. So through the sides, or excuse me, though the sides between these 2 polygons, though the sides increase in length, and of course I'm talking about increasing, I did the large polygon divided by the small, so I'm kind of like saying that, if I take all these measurements of the small polygon and I multiply them by 1.7, then this polygon here, all those lengths increase by a multiple of 1.7. I'm kind of adding this in as a little bonus. This isn't in my section of the textbook I am teaching out of, but we are going to ultimately need to understand the relationship. What happens when you take a figure, whether it's a two-dimensional figure like this, or eventually we'll be talking about volume with three-dimensional figures, and increase their size? Well, if I increase, if these are indeed similar figures, which means they have to be the same shape, and I have the scale factor of 1.7, then it's a two-dimensional figure, so it's kind of getting bigger by a multiple of 1.7 in two directions, in two dimensions. So the area inside this quadrilateral, if we were to find it, would not be 1.7 times greater than the area of this polygon, because it got 1.7 times greater in two dimension to keep the same shape. So actually the area is going to increase by 1.7 squared. We'll eventually get into a section in our book where we look at how the sides of two-dimensional and three-dimensional figures change, and then have to understand how the area and volume is changing based on how we're changing the lengths of those sides. With similar figures, we have the same multiple of change in two directions, two dimensions, and thus that is how the area is going to change by 1.7 squared. Okay, so that's the end of this page. Let's get on to our examples. Again, we're doing 5 examples. I'll try not to talk too much through them, but of course I do want to make sure you understand them as I go along. Let's get those started. First two. Example, triangle ABC is similar to triangle EDF. I have not drawn them in the same orientation this time to add a little level of difficulty. And I want to solve for the unknown values here. Now I've got two unknowns. I have an x marked here and a y plus 1 marked here. So I'm going to actually do 2 examples from this one diagram. Well, they're not in the same orientation. I've drawn it so that specifically, we have a side that looks the longest and a side that looks the shortest, and the same over here. So that might help us know what the corresponding sides are. Also, you can get that from the name. Now, over here I see that my first triangle is labeled ABC, and over here my second similar triangle is EDF. Well, AB, side AB, and side ED must be corresponding sides. BC must correspond to side DF. That side AC must correspond to side EF, and I have my drawings to back that up. Now, if I look at AB and I look at ED, AB is a length of 3 and DE is a length of 7. So I actually know both of those corresponding lengths, and that is how we're going to begin setting up our ratios to solve this problem. Now, as I set up my ratios, if I don't go in the same direction as I set up each of my fractions, then I'm going to get wrong answers. So I'm going to show a little arrow here indicating I'm going to connect the sides of 3 and 7 together, and I'm going to do all my ratios going from left to right to make sure that I have them set up with the same pattern and I get the right answers. So we have 3 over 7 is equal to, and let's not do the hardest one first, we have BC here, and that's the last 2 letters of my name in my triangle here, and that has to correspond to DF. So the x is going to get paired up to the side of 9, or the corresponding side of DF. So we have 3 over 7 left to right, x over 9. We're going to recognize that we have one fraction on each side of this equation, so we're going to solve that with cross multiplication. We have 7x is equal to 3 times 9, which is 27. Don't, I see sometimes students with these cross multiplications write a fraction after the cross multiplication. Keep the equal sign in the middle to make sure that you get the proper step to finish solving the question. Students that try and shortcut the work all the time will leave the equal sign out, automatically write some kind of fraction, and then half the time get the answer right and half the time get it wrong. We're going to undo this multiplication of 7 by dividing by 7, and x is equal to, yes, I do break my chalk a lot, 7 and, let me see here, 7, 14, 21. So there's 3 7s in there. 3 times 7 is 21. That leaves me with a remainder of 6 sevenths. So x is equal to 3 and 6 sevenths. Now, I want to now solve for y. you know, like, first of all, this is going to be a run-on decimal, I believe. And, you know, I don't believe I made a mistake. I can check it. And if I was looking at the right sheet of paper and realized that, yes, I'm right, but, you know, that's my own personal scratch work. What I guess I'm saying is, with you, as you do these problems with, you know, where you can set up multiple equal ratios out of the same diagram, if you use a number that you came up with yourself, that's fine, unless that number is wrong. You don't want to carry it into the second part of your problem and carry through that mistake and possibly lose more points on your test. So I'm going to keep using the 3 and the 7, the two known values that I was given in the first place. And then if I did something silly on this part and got some kind of wrong answer, I'm not going to continue that through the second part. You know, even if we know what we're doing, sometimes we hit the wrong button on the calculator or do something wrong in our head. So 3 and 7, now I'm going to match up the 5 with the y plus 1. Again, cross multiply. And I like to do the part of the cross that has the variable in it to keep it on the left-hand side. I like to do that first. Not required, just more often than not, I see my students get answers right when they keep the variables on the left, if they have a choice. 7 times 5 is 35. We're going to distribute that 3 through the parentheses. Undo that addition of 3 with the variable by subtracting. Undo that multiplication of 3 by dividing, and we get y is equal to, well, 3 times 10 is 30, and 30 out of 32 leaves me with a remainder of 2, and we get 10 and 2/3. And let me just check my work. Yes. I always like to include some fractions in my examples because, you know, they're easy to struggle with. So our two values here, our two unknowns, are x is 3 and 6/7 and y is 10 and 2/3. And that's the end of that example. Woo! Coming on over here, we have a very similar type of problem. We're going to do the same thing with the cross multiplication and setting up our equal proportions, but it's a little bit difficult with this kind of a problem. The 7 is the entire length of the small triangle that's nested inside this big triangle. So the 7 is an entire length of a triangle. The 4 is an entire length of this small inside triangle. And the 6 is an entire length of this large triangle around the outside, where the x is only a little tiny piece. If I try and set up an equal ratio or set up equal proportions with this diagram, I'm not going to get the right answer if I don't recognize that this x is just a tiny little piece and all these other parts are complete lengths. So a very, very strong suggestion when you're doing problems where you have similar figures nested inside of another one, it's much easier to know how to set up the problem correctly if you draw them separate. Someone pause the video and do that for us right now. Or right now. Now, if you get these problems right all the time, drawing these two diagrams separate is really not necessarily maybe worth your time, but to a lot of students they are. So I've got these two triangles drawn out separately now. I got a little crooked there with my side, but again, the whole point of this is just to make sure that I see what sides are actually corresponding, that if I have measurements that are all full lengths of the sides of the triangles, that I don't use a length that's just a piece of a triangle. And so to set this up, let's go left to right again. The 4 clearly is corresponding with the 6. The 7 is corresponding with the 7 plus x, and we get 4 over 6 is equal to 7 over 7 plus x. Cross multiply that. And we get 4 times 7 plus x is equal to 6 times 7, which is 42. Let's distribute that 4 through the parentheses. We get 28 plus 4x is equal to 42. Undo this positive 28 by subtracting it to both sides of our equation. And we're running out of room, so let's bring it up here. We got 4x. Let's see here, 42 minus 20 is 22, and 22 minus 8 is 14. And we're going to divide both sides by 4. And again, giving you some decimal fractional answers here. 4 times 3 is equal to 12. Take 12 out of 14, that leaves you with a remainder of 2, and we have 3 2/4, which reduces to 3 1/2. And that is the end of this example. I got a couple more coming up for you right now. Here we go. We have another set of nested triangles together. Now I went ahead and I've drawn these triangles separately and identified this full length here of the large triangle as having a length of x plus 6 by simply adding these two parts together, the segment addition postulate, and 5 plus 2 is equal to 7. Now, we can use these two triangles to, of course, set up our equal ratios and solve for x, just like we did in the last problem, but it's not necessary this time. Because if you look at our diagram, the x is just the sort of like last part of this segment that finishes up the big triangle. And the 2 is also just a portion of that side. So with this particular problem, we can set up our equal ratios, let's say, as going, you know, down to the corresponding parts and say that we have 6 over 5 is equal to x over 2. Where we're going sort of like from top to bottom, like top to bottom for the small triangle and top to bottom for the large triangle, but we're just using those tiny little pieces of the segments that finish up the entire lengths that make up that triangle, that large triangle. Now, again, it's okay to do that with this particular problem because the x and the 2, you know, they're like parts of the large triangle. It's not like the previous example where I had 3 full lengths and only one, number that was just a part of a length. When we do this, we're going to get 5x is equal to 6 times 2, which is 12. We're going to divide both sides by 5 to undo that math operation of multiplication, and we get x is equal to, let's see here, 2 times 5 is 10. Take 10 out of 12, and that leaves you with the remainder of 2. So it's 2 2/5. Let me just check my own work here, and we're good to go. Over here on this example, this is similar to the last example I did in my previous video, but we're going to tie it together now with similar figures and do just sort of like add another step to it and relate, you know, a given triangle to another one. We have a triangle with sides that have lengths that are in the ratio of 4, 5, and 6 with a perimeter of 60. So basically what we have is a triangle. I don't know what the sides are, but we have 4, 5, and 6. They can't be the sides of, they can't be the lengths of 4, 5, and 6 because then the perimeter only add up to 15. But the perimeter is supposed to add up to 60. So we're going to let those be unknown lengths, but have it be 4x, 5x, and 6x with that common scale factor on each of those three sides to allow this, you know, the size of this triangle to either increase or decrease to match that perimeter of 60. So we have a triangle with this ratio with a perimeter of 60, a similar triangle, which, you know, I don't know if it's going to be larger or smaller, but we have another similar triangle whose longest side is 18, and I think it's pretty safe to assume that, you know, if x is the same for all of these sides, that the 6x is going to correspond to the longest length. So this other second triangle has a longest length of 18, and we want to find the length of its shortest side. Now we have 6, 5, and 4x, so this is going to be the shortest side. Corresponding to that is going to be this other triangle whose shortest side is what we're going to be trying to find. So I'm going to just put an empty box there indicating that I want to know the length of that. I'm probably going to run out of room, so let's first figure out the sides of this first triangle that has a perimeter of 60. Well, these three unknown lengths have a perimeter of 60, which means they have to add up to 60. So we have 4x plus 5x plus 6x is equal to 60. We have 4 and 6, just adding like terms now, 4 and 6 is 10, and 5 is 15, so we have 15x is equal to 60. Divide both sides by 15 again to undo that multiplication, and we get x is equal to, let's see here, 15 times 2 is 30, oh, and 30 and 30 makes 60, so 60 divided by 15 is equal to 4. let's see here, 4 times 10 is 40, 4 times 5 is 20, 40 and 20 do make 60, so my answer is correct. So this triangle here has sides of 4x, and 4 times 4 is 16. 5x, well, 5 times 4 is equal to 20. And 6x, well, 6 times 4 is equal to 24. Okay, well now with that work out of the way, let's find the shortest length. So let's see here. The 24 is corresponding to the 18. So I'm going from large to small, or from top to bottom as I've drawn my diagram. That means that 16 is going to correspond to my unknown length of x. Again, stay in that same direction, so we have 16 over x. We got one fraction equal to one fraction, so we can solve that with cross multiplication. We have 24x is equal to, right off the top of my head, we have 18 times 16 is 288. Right off the top of my head. We're going to divide both sides by 24. And probably should have picked a different variable since we had x related to this first triangle up here, but I kind of erased all my work and kind of just started to go from there. So hopefully you realize that this x is kind of like another x. That's bothering me a little bit. Let's call that y, so it relates to the other triangle. And we're going to solve that for y. Divide both sides by 24, and we get y, which is the shortest length of this other similar triangle, is equal to, let's see here, 288 divided by 24 is equal to 12. Boom. Alright, so that's the end of my last example. I got a couple of just sort of quick wordy examples. I'm not going to have to work through them, just sort of kind of like a true-false statement and give a reason why. We'll be done with this video. The last two true-false statements, your textbook wouldn't give you the diagram to go along with these, but for explanational purposes, any two regular hexagons are similar, true or false? Well, that would be true. Because regular polygons have all their angles and all of their sides are going to be congruent, then the best I can here, I've drawn two regular hexagons, and they are similar. Why? Because, well, they're all going to have the same interior angle. All their corresponding angles are going to be congruent because they're both regular hexagons. And the fact that all of these sides have to be equal within this hexagon and all these sides have to be equal within this hexagon, when I set up that first ratio or that first proportion for the corresponding sides, I'm guaranteed that all of the proportions for the corresponding sides are going to be congruent, and thus they are similar. A rectangle is similar to any square. Any rectangle is similar to any other square. Well, that's going to be false. A rectangle and a square, they both have four sides. They both have all of their angles being 90 degrees, so we've got the first requirement met, that all of the angles are congruent. But when I set up the proportions for all the sides, and you can already see that my example here, I have not drawn two figures which are the same shape, and mathematically what's going to happen is if I take this side and I try and divide it by this length, so I set up a proportion for the corresponding side, so this length divided by this length, that is not going to be equal to, if the shapes are different, to this length divided by this length, because, well, you can even see that the proportions are different. And mathematically, those proportions are not going to come out to be the same, and thus, of course, like I've already said, it's false. So, that's the end of this video. I'm Mr. Tarrou. Go do your homework.